Hello, everyone. Welcome back to Math 221. A little bit of news for you. Your first exam is going to be next week on April 21st, so Wednesday, just like the dates of the rest of our quizzes. The exam is going to be formatted similar to the quizzes. You'll have, I'm going to upload a PDF in the morning, and you'll have all day to do your problems. Obviously, it's going to be longer than the quizzes given that's an exam. Um, but you'll have all day to work on it and get your PDFs in by midnight. One thing, make sure that your PDFs are a single PDF rather than, each photo is converted to an individual PDF. Um, I'm not going to dock any points if it's not a single PDF, but it does make the grading process for me a little bit easier that way. The exam is going to cover the first 3 weeks of material. Obviously, this is week 3, right? So everything we cover this week will be on the exam. There will not be any lectures uploaded next Tuesday, right? In a normal class, the exam would take the whole time, so there wouldn't be any lectures, right? So no lectures on Tuesday, um, exam on Wednesday, and then content will resume next Thursday. Um, with that little bit of bookkeeping out of the way, we can jump right in back to the story of calculus. We've got sort of two main topics today that are fairly disjoint. Um, but the first one is a thing called marginal analysis. Okay. And marginal analysis answers a question that maybe has been kicking around in the back of your brain. Um, so we spent last week developing the derivative. We spent the last, 2 weeks developing calculus. And the question that I'm sure is in a lot of your minds is like, why does this matter? Right? You're in this class because you have to check it off for a prerequisite. It's a thing that you need to take for your degree, and you're just here to do that. And maybe some of you believe me when I say that, math and especially calculus is like weightlifting for your brain, right? It trains those logical thinking muscles. Um, and that's all well and good if you believe me, right? And I know that a lot of people don't, and that's fine. Um, but the question that I'm sure is kicking around is like, okay, but like still why? Like surely there's other ways to train these logical thinking processes, right? Like, that's what puzzles are for. That's what, in a lot of sense philosophy is. Like why specifically calculus? Um, and marginal analysis gets at a like tangible application for the tools of calculus. Okay, so marginal analysis, in its most basic definition, is the study of the rate of change of economic quantities. Right now, that's a little bit of a mouthful, and you'll notice it does have the really nice rate of change word, which is what calculus is concerned with, right? But here's sort of the idea, right? Um, Economists care about the GDP of a country, right? Um, but equally, if not more than the GDP, they care about how the GDP is changing, right? Is it growing? Is it declining? Those matter a lot, right? Similarly, someone who's manufacturing goods, right? Um, they're not just interested in how much it costs to produce a certain quantity of some item, some commodity, but they're also interested in how that total cost changes if they change the production, right? So if they increase production, does their total cost go up or down, and does their average cost go up or down, and by how much, right? Those are where the tools of calculus can kind of start to shine a little bit, right? Um, let's sort of look at a very basic example, and see if we can look at why this word marginal might be applicable, right? So, say you're manufacturing something, I don't know, say refrigerators, right? That's the example they use in the book. Um, and your total cost in dollars each week, right, um, is modeled by 8,000 plus 200x minus 0.2x squared with this, our domain restriction, right? And then x is going to be our numbers of refrigerators made, right? So one of the things that we can ask, right, is how much does the 251st fridge cost, right? And the simple way to calculate that, right, would be the cost of 251 total fridges minus the cost of 250 total fridges, right? And the 250 is going to cancel with 250 of these, and then we're going to get the cost of just the 251st, right? And so what's that going to end up with? Well, we're going to have C of 251 is 8,000 plus 200 times 251 minus 0.2 times 251 squared minus C of 250, which looks like this, 250 squared. When you work out that math, you get 45,599.8 minus 45,500, right? Which means the 251st fridge costs $99.80. Okay. I want to compare this to the derivative at 250. Okay. That may seem a little bit strange. Okay. But here's the idea, right? If our rate of change of the total cost function is going to mean anything, well, it should approximate, right, how much it costs to manufacture another fridge, right? So what's C prime of x? Well, we're taking the derivative. The 800 is going to drop. We're going to get 200 minus, going back here, this 2 is going to drop down, and so we're going to get 0.4x. Okay. What happens if I plug in 250? Well, I'm going to get 200 minus 0.4 times 250, which is going to be 100, right? So it's $100. Here's what I want you to notice, okay? If we grab some section of a parabola, right, it's going to look, with the domain restriction, it's going to maybe look something like that, okay? Here's what I want to draw your attention to, okay? When we're calculating how much the 251st refrigerator cost, right, what we're doing is we're calculating 250 plus 1, in this case I'm going to call it h, minus c of 250, and then we're dividing by h, right? This would give us the average cost, right, of adding so many refrigerators, right? The average cost per refrigerator. But this looks an awfully lot like the derivative, right? What this is this is giving me a secant line through my cost function, right? Something like that. Now, in practice, sometimes this can be difficult to calculate. Instead, what we can do is we can analyze the derivative. And the derivative is going to approximate the secant line, right? Just as when we were developing the derivative, we use the secant lines to approximate and get closer to our derivative, which means that the reverse is the case too, right? A derivative can approximate a secant line. And so we can use these tools of calculus to look at these ideas, and rather than having to calculate all of these secant lines and deal with things that ended up, in the 50,000s, we can use the secant line and get a really good approximation, right? 100 versus 99.8. It's going to get you the idea, right? That's sort of why we're doing this, right? Is it's getting you the behavior of our function, okay? So this is then going to lead us into a couple of definitions, right? So if you're in the business of, producing some sort of commodity, right? Then the actual cost incurred by producing one more, right? Say you make 250 and then you make one more. That's called the marginal cost, right? And that's obviously very important if you're running any sort of these plants, right? However, we just saw that we can approximate it by looking at the rate of change of the cost function at that point, right? And it's for that reason, right, that we define the marginal cost function right? The marginal cost function, and it's defined simply, right? It's the derivative of the total cost function, right? It allows us to get an idea of these, marginal behavior by looking at the total cost function, right? In these applications, right, the word marginal becomes synonymous with derivative of, right? And so marginal analysis and marginal functions are, well, studying the derivative. So we can take a look at another example, right? Say you're once again manufacturing some commodity, right, with a cost function of, I don't know, 0.0001 x cubed, right? One of the things about building real-world models from data is your coefficients are often a little bit messy. Okay, but say this is the function that you end up with when you analyze your data, right? So here's what we can do, right? We can find the marginal cost function of this fairly easily, right? It's just taking the derivative, okay? Our 3 is going to drop down. We're going to get 0.0003 x squared minus our 2 is going to drop down, and we're going to get 0.16x minus 40, and then our 5,000 just being a constant is going to drop, okay? So this is our cost function, plain and simple. And one of the things that we can do right, is we can plug in um, a number of different values to see how um, our marginal cost function and what that, or rather see how our marginal cost function behaves, which will tell us about the total cost of manufacturing of those goods, right? So we can say calculate, C prime of 200, we'll go 300, we'll go 400, and 600, okay? And you would calculate this by plugging in 200 here. With these, ugly numbers there, you'd most likely use a calculator. So I'll just tell you what the results are here. We get 20, 19, 24, and 52. Okay, we get 4 two-digit numbers. And one of the things that we're interested in is, like, what do these numbers mean, right? Can we learn anything from them? And if we keep in mind what the marginal cost function tells us, we absolutely can, right? The marginal cost function approximates the additional cost to manufacture one more, right? So if we're making 200 of whatever this commodity is, right? If I were teaching this in person, I'd, have you guys tell me, say we're making, I don't know, dish rags, right? One of the things that I did during the pandemic when last year when there were no paper towels, is I just bought like 60 like hand towels, and I have a functionally infinite supply of them now, right? So say you're manufacturing hand towels, right? For the people like me who just buy a ton so that they don't ever have to worry about them, right? Um, so that means that if you were to manufacture 200 of these, gray dish towels, then manufacturing one more would cost $20, right? And, maybe dish towels aren't the best example of this given, the prices that we're working with, but I think the idea holds, right? Um, so it's, $20 per, for the next one, right? Not per additional, but just for the next one, it's going to be about $20, right? If you instead are manufacturing 300, right, then the next one's going to cost approximately $19. So this is important, right? If you produce a bunch more, your average cost per next one goes down. So you think, well, let's make 100 more. Surely it's going to keep going down. But then you make 400, and your approximate cost of making the next one goes up to 24, right? Go even crazy, go up to 600, and the actual cost of producing one more is about $52. All of a sudden, that's way more expensive, right? And there's all sorts of things that could be causing this, right? More overtime, you need more maintenance, you're more likely to break down, based on how you're running your machines or whatever. But that's sort of how you would use this marginal cost function to analyze what your cost function is telling you beyond just this is how much it costs, right? Well, we can approximate, some very, very useful information here, okay? There's another similar idea that I want to expose you to next. And so it's very, very closely related to this idea of marginal cost, okay? But first, I want to introduce you. So there's this thing called the average cost function. Okay. And we'll say if C of x is a total cost function, then the average cost function is, so it's written like this, C bar of x, so it just has this straight line, okay? And it's your cost function divided by x, right? So it's you know, the average cost is, well, the cost to produce everything divided by how many things you produced, right? It's fairly, you know, a simple idea, right? But there's also the marginal average cost, and it's C bar prime, right, of x. And it's going to measure the rate of change of the average cost function with respect to the number of units produced. Okay, so say once again, you know, you have some cost function. So it's 400 plus 20x, right? And let's say this represents, I don't know, you're manufacturing chess sets, right? I've been playing a lot of chess in my spare time recently. And like I said, I don't have, you know, an actual class here to shout out ideas. If you have, you know, specific commodities that you think would make good examples, shoot me an email and I can just have like a running list from you guys to, you know, randomly pick from for, you know, things that these functions can represent. But say this is our cost function for chess sets, right? And let's take a look at the average cost function, right? So C bar of x is C of x over x, right? So it's going to be C of x over x. And we can split this up, right? Because fractions will break over addition in the numerator, right? This is going to be 400 over x plus 20x over x. Those x's are going to cancel, and we get 400x over 20, okay? C bar prime of x, right, our marginal average cost function, this 20 is going to drop, right? We have 400x to the negative 1, right? That's what an x in the denominator represents. Our negative 1 is going to drop down, and we're going to get negative 400. Negative 1 minus 1 is negative 2, so we have negative 400 over x squared, okay? So what this means, right, is because the marginal average cost function is negative for all of the values of x for which this would make sense, right? It wouldn't make sense to ever put a negative value of x into our cost function, right? That means that the rate of change, right, is negative for all of our valid x's, right? So what that means is that C bar of x decreases as x increases. Additionally, if we look at the graph of C bar, right, in particular, the part of the graph that, you know, matters to us, the positive values of x, we're going to see something like this, right? Notice that the limit as x goes to infinity of C bar of x equals 20, right? This guy is going to drop away, and we're just going to be left with a 20. And you know, like this makes sense with sort of what we're looking at here, right? Our average cost as we get very large is going to approach 20, right? Because it's a fixed $20 per unit plus 400, right? And as x gets very large, this 400 is going to matter less and less and less, right? And we can get this sort of information from the graph of our average cost function. And then our marginal average cost function is going to tell us, even before we graph this to look, that our average cost is always decreasing, right? Whenever you manufacture more, the average cost decreases. And that's told to us directly here, okay? Now let's take a look at another example. Let's take a look at another example, right? Let's x cubed. Let's take a look at our gray dish towel cost function, and sort of look at what the average cost function information tells us here, right? So we have c bar of x, right? C bar of x is c of x over x. So we get 0.001 x squared minus 0.08 x plus 40, and we have 5,000 over x, okay? And what we can do is we can take the derivative of this, right, to get our marginal average cost function. So we get 0. Need one more 0, 3 zeros to x, right, minus 0.08. My 40 drops. We have minus 5,000 x squared over x squared, okay? And here's one of the things that I want you to notice, okay? And that's that c prime, or c bar prime, sorry, of 500, right? If you work through this calculation, c bar of 500 equals 0, okay? And that's important, right? And again, probably at the end of next week after the exam, or maybe the week after, we'll go into a lot more depth about analyzing the significance of a derivative being 0. But in the meantime, why don't we sketch this graph, okay? One of the things that I want you to notice is that as x approaches 0 from the right, this is going to get arbitrarily large, okay? And we don't need to worry about negative values, okay? And if you were to plot some points, you'd see some behavior like that, okay? And we can go through, curve sketching and, plotting some points to get these ideas. All of that was covered in 118. The important part that I want to draw your attention to is here. So right here at 500, if you were to plug in 500 to c bar, right, this is c bar of x. I guess it's y equals c bar of x. There's a point, say right here, that's 500, and 35 is what the average cost is. And the derivative at that point is 0, which means the slope of the tangent line is flat, okay? And here's what that tells you, right? If you look at the behavior of our derivative around this point, right? Before, if we were to plug in values to our c bar of x, we would get a negative derivative, right? The average cost is decreasing, and honestly decreasing pretty quickly. As soon as we get past 500 units, our average cost goes up, and goes up, pretty quickly as well, right? This is the behavior even that we saw when we were analyzing the marginal cost function of C of x, right, was the average cost of adding one more, or the approximate cost of adding one more, increased quite substantially as you got larger and larger. Well, the same thing appears to be happening here with our average, or with our marginal average cost function, right? After 500 units, the average cost shoots way back up. So if you have this data about the gray towels that you're manufacturing, well, you shouldn't manufacture more than 500 a week, right? All of a sudden, your average cost is skyrocketing, and unless you have like other reasons to do so, and you might, but if this is the only data you have, you should be right there, right? That's how many you should be making, or at least that's what this analysis says, right?